Climate is not only variable spatially, but also varies at almost all temporal scales. Temporal variability in climate is a major factor that affects ecosystem functioning. Here, we'll begin to examine some of the factors that impact climate across a range of temporal scales. In this section, the authors state that millennial scale climatic change is driven primarily by changes in the distribution of solar input and changes in atmospheric composition. So the scales of change that we're talking about now are on the thousands of years, not year-to-year variation, but changes in climate that occur on much longer timescales. Now, the study of the ecology of the past of ancient systems is called paleoecology. And in addition to paleoecology, there's also paleo-ecosystem ecology. Now, this is not necessarily a large subdiscipline of ecology, but there are people out there that are trying to reconstruct the ecology of ecosystems in the past. In addition, there's paleoclimatology, trying to understand the climates of the past. And all of these come together in understanding the ecology of modern ecosystems. Now, as we said, climate can change on multiple timescales. And one of the things that people have reconstructed is how the climate of the Earth has changed on millennial timescales. For example, what are known as Milankovitch cycles are important components driving the climate on these timescales. Milankovitch cycles are changes in three components of the Earth's orbit around the Sun. So, for example, the eccentricity of the orbit around the Sun changes on 100,000 year timescales. So sometimes it can be very eccentric and drawn out, other times not quite so much. In addition, the tilt, the angle of the Earth relative to its orbit changes too. Currently it's 23.5 degrees, but sometimes it can be more extreme and less extreme. In addition, there's precession, which is kind of a wobbling of the Earth on its axis, which changes which hemisphere is going to be facing the Sun at different points in its orbit around the Sun. Now, the authors state, for example, that ice ages are triggered by minima in northern high-latitude summer radiation that enable winter snowfall to persist throughout the year and build northern hemisphere ice sheets that reflect incoming radiation. So this is a point where precession is important. So as you can see, that at different points in the orbit around the Sun, the Earth is at different distances from the Sun. And precession determines whether the northern hemisphere is facing the Sun when the Earth is relatively close to the Sun or relatively far away. And ice ages follow precession in many respects, but are also impacted by eccentricity and tilt. The consequences of the Milankovitch cycle and changes in the radiation balance of the Earth can be found in long records of the relative abundance of different species that we see. So, for example, this is from Jock McAndrew's work that was published in 1966, and this is a pollen profile from a bog in northwestern Minnesota. And what we can see here is that the scale on the y-axis is thousands of years, and this is a roughly 11,000 year record. On the x-axis for birch, alder, fir, pine, elm, and oak are the abundance of pollen that's found in different sediments. So, for example, 11,000 years ago, there was a lot of pine, but not a lot of alder or elm. And over time, these abundances changed. And you can see at 8,000 years ago, there was a shift to more of an oak-dominated community. And at roughly 4,000 years ago, a shift to a birch and then back to pine. And what this represents is changes in the temperature as well as the precipitation that was present in the climate. And these are changes that occur on thousands of years that are associated with changes in the orbit of the Earth around the Sun. This is actually one of the bogs that Jock McAndrews had worked on and accumulated pollen records from over 50 years ago. This area you can see is currently a bog. And in the peats that formed below the bog and in the sediments that are adjacent to the bog in the open water, is a long record of the vegetation community. Now this is actually a bog that we had cored in a slightly different manner than Jock McAndrews had, but you can see essentially below us are peats that accumulated, and we'd used a corer in this place, had a long tube down below that we could use to sample the sediments and the peats below us. And when you pull them out, they look something like this. And this is a record of approximately 500 to 1,000 years of accumulating organic matter. And inside that organic matter, you would find lots of things. You'd find little parts of plants, for example, as well as other things that had accumulated in the surfaces and then had become buried. One of those things are pollen grains. And when you take a look here, this is an example of Helianthus pollen. A lot of these pollen grains you can identify to the individual species or genus. And that's exactly what Jock McAndrews had done in this bog to show us that 11,000 years ago, the area was surrounded by pine. And then, as the climate had dried out, presumably, oaks had become a lot more abundant. And then, more recently, the climate had become moister and somewhat cooler, and pines had begun to dominate again. Now, in addition to these millennial scale cycles, we can also have interannual cycles in climate. An example of that is the La Nina, El Nino patterns that we find in climates throughout the Pacific Basin. And essentially, there are different phases of circulation in the ocean that drive different patterns of climate in the surrounding areas. So here, for example, are the conditions during a La Nina. And during the La Nina, there's a relatively large area of cold water that forms off of the Pacific coast of South America, and warm water that forms in the western Pacific off of Australia and Asia. And where there's warm water, we're going to get a low pressure system and a lot of moisture that's going to form in those areas. That area, it's going to lead to circulation patterns that have high pressure systems in the eastern Pacific that bring relatively dry times to this area. During an El Nino event, which is not necessarily considered the normal conditions, we have a different pattern where we get warmer water that tends to slosh over in the eastern Pacific, which reduces the high pressure system that sets up and produces a lot more rain. The rains that normally would fall, the heavy rains that would normally fall in Asia on that side of the Pacific, are a lot weaker. And instead, we're getting a lot more precipitation in the central part of the Pacific. El Nino and La Nina events look something like this. These are sea surface temperature anomalies, so basically patterns of temperature more or less than normal. And this is what an El Nino looks like. And we talked about how there is an area of warm water that forms in the eastern Pacific. And if you look here on the west coast of North America, you can see a lot of warm water that have formed here. Where there's warm water, you're going to get a lot more evaporation, and you're going to get a lot more rain in the adjacent areas. During the La Nina, you can see that it's a lot colder in those areas too, 3-4 degrees Celsius. Same thing when you take a look off the western coast of North America. And these colder times are going to bring high pressure systems and a lot less precipitation during those times. These are typical January through March weather anomalies during El Nino and La Nina. And again, during the El Nino, that's when we had a lot of warm water that would pool off of the western coast of North America. And low pressure systems would set up in the northern Pacific. We get warmer temperatures here and a lot wetter conditions in this part of North America. During the La Nina, these waters are a lot colder. And as a consequence, we're going to get a lot less precipitation that falls here. These are cycles that last on the order of a couple years, 5-10 years often, and produce climate variability for the surrounding ecosystems. Now, in addition to these annual patterns, or annual scale patterns of climate variability, we also have seasonal and daily patterns. And these seasonal patterns, again, are relatively short, too short to be considered climatic variation as much as weather variation, but they're still really important for thinking how these ecosystems function. So the authors use examples of how in lakes, we're going to see differences in the vertical and horizontal mixing of waters dependent on how much wind is blowing in the direction that it's blowing. And again, these are patterns that change on the order of hours to weeks. And again, changes in insolation or cloudiness too, that can vary on scales less than a year. And these patterns really affect how much vertical mixing there is. So for example, if you get a big storm, you're going to have a lot more vertical mixing in the upper layer, that epilimnion, and probably a lot less of effect in the hypolimnion. The scale here is on the order of tens of meters for the y-axis, but tens of kilometers for the horizontal axis here. So in all, it's important to remember that climate and weather vary on a range of timescales. And this is part of the ecosystem functioning. Weather and climate are variable on a multiple set of timescales, ranging from hours to days to years to millennia. And all of this is important for thinking about ecosystem functioning. The current structure and function that we have in ecosystems is derived not only by the current set of weather and current climate conditions, but the weather and climate conditions of the past too. And all of these are variable and important to understand when we're trying to understand ecosystem processes.